How about? So remember with this one, we had this picture. The variables here are theta and x, right? And these are fixed length. So this is the important triangle we've got with the variables in it. We called that x. We called that theta. They gave us some information, so we're able to write down some snapshot values, right? They told us that at this snapshot, this frame in the video, theta is equal to pi thirds. And they told us that this crankshaft is rotating at a rate of 200 revolutions per minute. And so we converted that into radians per second. So now we've got theta and theta dot, and we were looking for, what was it we were looking for? The velocity, right? So what's velocity here? What's that mean? It says find the velocity of the piston. What's that going to be? Must be a rate. If it weren't a rate, we wouldn't even need to do calculus on this, right? So what rate would that be? What would the units of velocity be? Inches, in this case, inches, yeah, inches per second, because we're measuring distance in inches. Time, I guess we're going to use seconds, right? So inches per second. So what would that match up here? What rate? We've only got a couple options. We got x's and thetas, right? So what's it going to be? What do you think, Shay? What's velocity going to be? Rate of change of which variable? Okay, any ideas? What would it be? X dot, sure, right? Because x is this distance right here. So the rate at which that distance changes is how fast that piston is moving, right? Does that make sense? Okay, so then we're looking for x dot. So we've got to relate x's and thetas. And so how do we do that? Well, we've got this triangle, but it's a non-right triangle. So we can't use Pythagorean theorem. We've got to use the law of cosines in this case instead, right? Law of cosines tells us b squared equals a squared plus c squared minus 2ac cosine theta if this is how we're defining the sides and angles in that triangle. Well, if we match these up, this is kind of where we left off. If we match these up in the law of cosines, the A is really represented, that becomes a 3, the B becomes a 7, and the C is our variable x, right? And then theta is theta. So we ended up with this equation then. That's what the law of cosines gives us for our triangle. Okay? How we doing? Give me 1 to 5 on that. Is that good? Okay? Okay, questions? Okay. Now what? We got our parent equation. Now what can we do? I guess we can clean that up a little bit, right? Let's go ahead and simplify. So that's 49, that's 9 plus x squared minus 6x cosine theta. Okay, now what? Say it again. Solve for x. Okay, what's our reasoning for that? Okay. I mean, we could. When you say solve for x, like what would that involve? Just isolating the x and say it again? Okay, so moving the cosine theta to the other side. Okay, we could do that. We could. There's solving for x is going to be a little bit tough to do here, though, isn't it? Because look, I've got an x squared term and an x term, and the x term has a cosine in it. So that's going to be that's a tall order. That's going to be kind of tough to do. And being as we're trying to find x dot, there's really no reason for us to do that, because when we implicitly differentiate, the x dots are just going to pop out of each term where there's an x, right? See what I'm saying? And then it's going to be much easier to solve for x dot, which is linear, than it is to solve for x here, where x is quadratic. You guys get what I mean by that? Okay, so really, when we're doing related rates, we don't want to do the solving part until the very last step after we've implicitly differentiated. Okay? The other thing, too, is remember also that we can't plug in any of these snapshot values until after we differentiate, right? If we did plug in values for the variables now, when I differentiated, those would look like constants because they'd have number values instead of variable values, right? And when we differentiated, they would go away because the derivative of a constant is 0. Okay? So we can't do that either. So what is our next step then? Differentiate implicitly with respect to t, right? So if we do that, what's that going to give us? What's the derivative of 49 with respect to t? 0. And then I'm going to get 0 from the 9 also, aren't I? Derivative of x squared. Okay, good. 2x, x dot. And then here I'm going to have, let's go ahead and just group, how about the 6x together? Why not? Okay. When we're doing product rule. Because look, I've got x's times cosine thetas here, right? So I'm going to have to use product rule. So I'm going to subtract whatever I get from the product rule. Okay, so what's that going to give me? If I've got 6x times cosine theta. Okay, so I've got 6x times the derivative of cosine theta, which is negative sine theta, theta dot. Everybody get that? Derivative of cosine theta is negative sine theta, theta dot. Okay? Plus cosine theta times the derivative of 6x, which is 6x dot. Okay, good. So it's giving us 6x dot cosine theta. Make sense? Okay, we could distribute that negative sign, and I'm going to get 2x x dot plus 6x sine theta, theta dot minus 6 cosine theta x dot. Okay, now remember we just got to isolate the x dot, right? Okay, so what I would do here, and there's no one way to do this. I would always prefer to keep signs positive. So what I would do here is I would push the x dot terms to the other side and leave this one positive. Do you have to do that? Not really. I mean, that's sort of nitpicky, but that's the way I would do it. The other thing we could do, I guess, real quick, we could divide each side by 2. So that goes away. That goes away. And that becomes a 3. And that becomes a 3. Okay. So then we'd end up, if I push these terms over to the other side, I'm going to get a positive 3 cosine theta x dot minus x dot equals 3 x sine theta, theta dot, right? And then last couple steps. Yeah, and what would the steps be to isolate x dot there? Yeah, factor it out and divide by the remainder. Okay, so if we factor out an x dot, on this side I've got my 3x sine theta, theta dot. I'm going to divide by whatever's left behind when I factor out the x dot, which would be a 3 cosine theta minus x. Everybody buy that? We good? Okay. Now it's time to plug and chug, right? Now they have x's in there. Do they give us a value of x? They do not give us a value of x, do they? Okay, so that's something we'd want to add to our list of snapshot values. But we could go back to our snapshot and we could take that triangle at that time and solve for x, right? So at the time of our snapshot, what does our triangle look like? So we've got our value of theta, which is pi thirds. We know this is 3, and that's 7. And then we would just use the law of cosines to solve for x, right? So what's that tell us? If we take this equation right here, and we solve that for x, because we know the value of cosine now, right? Is there not a better way to do that? Boy, that seems pretty tough. That's it. Yikes. Okay. So then if we solve this thing for x, what are we going to get? So I'm going to end up with 49 equals 9 plus x squared minus 6. And then the cosine of pi thirds is, what, 1/2? So this part, cosine of pi halves becomes a 1/2. Okay, so what's that give us then? X squared minus 2x. If I subtract the 49, I get a minus 40 equals 0. Double check me on that. Does that all make sense? Cosine of pi thirds is 1/2, yeah.
So then shouldn't it be x squared minus 3x?
Oh, 3x, there we go. Yeah, there we go. How'd I get? Why'd I put a 3 on the bottom? I don't know. Yeah, and that's going to be better. That's going to factor. That's way better. Okay, yeah. Okay, yeah, we can solve that by factoring, can't we? Okay, so what are the values of, how's that factor? There we go. X minus 8 times x plus 5. So we're getting the solutions x equals 8 or x equals negative 5. Now, which one of those physically makes sense and which one does not? Yeah, the 8. We can't have a negative length of a side of a triangle, can we? Right. So this one is non-physical. We can discard that one. It makes no sense, right? But we know x equals 8. So now we've got all the pieces that we need. So we can add that to our list of snapshot values up here. And now we could plug and chug. Okay? Does that make sense? And we would just, and at that point, it's just plugging in numbers and simplifying it, simplifying the result. Okay? Okay? Make sense? Any questions? Okay. Here are the other ones I had. I had an Isosceles Triangle one we can do. That's a really good one. You had one like this on the first assignment, right? Bug one. Was that on the first related rate assignment? Okay, how we do? Did you get that one, Shay? Skip that one. Do we want to go through this guy? Okay, if you've already done it, you can just work. But how about if I go through this one today? So bug is moving along the right side of a parabola, y equals x squared. So there's the parabola. Bug's moving along the right side of that at a rate such that its distance from the origin is increasing at 2 centimeters per minute. At what rates are the x and y coordinates of the bug increasing when the bug is at the point 636? Okay, so then what's going to be, if the bug is moving along this parabola, he's going to have coordinates x, y, right? Okay. The distance from the origin is increasing at that rate. Well, that's the distance from the origin right there, isn't it? Okay, if we call that capital D, what's going to be our parent equation then? I mean, what's the relationship between capital D and x and y? And I guess we know some stuff, don't we? We know we could write down our snapshot values. What's D dot? 2. Yeah, 2 centimeters per minute. Does that make sense? So D dot is 2. That's the rate of change of that distance between the point and the origin. Okay. And then we know a point also, right? We know the values of x and y. So we know this stuff right there. We know x equals 6, y equals 36. Okay? So what's going to be then our parent equation? Just a distance formula, isn't it? Right? So distance, we'd say that, or you could even think of it as the Pythagorean theorem with this triangle, right? Where this quantity is x and that quantity is y, right? And so we end up with d squared equals x squared plus y squared, right? If we decide to solve for d, then we just get the distance formula. D equals the square root of x squared plus y squared. Okay, so a couple things we can do here. One thing is, could we write d as a function of a single variable? Because that would make things easier. If I could write d with only x's or y's, that would make the calculus a little bit easier, wouldn't it? Is there a relationship here between x and y that we could use? That's it, y equals x squared. This point can't be anywhere out here in space. It has to be on this parabola, right? And all the points on the parabola have to have this relationship. Y has to always equal x squared, right? So we could make that substitution. If we let y equals x squared and we make that substitution, look what we get. We get d as a function of x equals the square root of x squared plus x squared squared. Okay, that helps a little bit, doesn't it? Right? And if we're looking ahead, after we solve for x dot and we want to find y dot, well, look, we could just go right back there and use that equation to relate those rates. Everybody see that? Do we have to do it that way? I mean, no, you don't, but man, it makes it a lot easier. Anytime you can get this parent equation down to a single variable, you always really want to do that. Okay. All right, so then if we differentiate implicitly here, what's that going to give us? So I'm just going to get d dot, right, equals. Now I'm going to think of this, I'm going to have to use chain rule, and that square root is a 1/2 power, right? So what's the derivative of hand to the 1/2? 1/2 hand to the negative 1/2. So the first step would be 1 over 2 times the hand to the negative 1/2 is just a square root on the bottom, right? So the square root of x squared plus x to the 4th. Okay, now we got to take the derivative of what's inside. Well, what's that going to be? The derivative of this stuff inside would be 2x x dot plus 4x cubed x dot, right? Yeah, good. So times 2x x dot plus 4x cubed x dot. And we could combine that into maybe just one fraction there. I could, a couple things, how about if I'm a little bit tricky here? What if I were to divide that 2 into both of those two fractions, right? Or into both of those two terms. Does that make sense? I have a 2 on the bottom, and I could factor a 2 out of the top and cancel that. So I could do, it'd look like this. Make sense? And then I could factor out an x dot, and then I would just end up with x plus 2x cubed times x dot on the top, and on the bottom, square root of x squared plus x to the 4th, right? Okay, and that's all stuff I know. Or yeah, it is all stuff I know. I'm trying to find x dot, and I know d dot, and I know x, right? So at this point, I could just plug and chug. I could plug in all those values and solve for x dot, okay? So what happens if we do that? X is 6, and d dot is 2. So, geez, what's that going to be? So I've got 6 squared is 36. 216 times 6, yikes, what's that going to be? 96. So 1296, I think. And so we get, and then I've got my x dot out here that I'm trying to solve for, right? So we just get 2 equals, that's a cubed, so 216, so that's 432. I think that's right. You guys better check me on this, but I think that's all right. There's no way that's perfect square, is it? Could we be that lucky? 1332 a perfect square? No, it's not. It's not. So we're going to be stuck with some weird number. So if I solve for x dot, I'm going to get 2. I got to multiply by the reciprocal. So 2 times the square root of 1332 divided by 438, assuming I didn't make a mistake in there somewhere. And that's going to give me about what? And then we want to see if this passes or if this seems reasonable too as an answer when we're done. I want to see if I just want to make sure. Well, it's almost irrelevant what it is. We can plug it into a calculator and get an answer. What did you get? Point 167. Okay. And our units are centimeters. Boy, that seems pretty. Oh, this is the bug one. So maybe I was thinking, yeah, maybe that's right. Bugs don't move very fast. So that's going to be centimeters per minute. That's his change in his x coordinate. Y coordinate might be a lot faster though, right? Because he's going to be moving mostly up. So we got the x answer. How would I get the y answer? I guess we got to do that part. This part's pretty simple, right? I've got this equation that relates y and x. That's my secondary equation. What could I do and what would happen if I differentiated that with respect to t? Right, so if I did that, aren't I just going to get y dot equals 2x x dot, right? And so I could plug those values in, right? So then I get y dot equals 2 times 6 times this weird answer. What was that? 0.167. Okay, so what is that, about 1/6? That's about, is that about 2? It's about 2, isn't it? Should be about 2. Is that right? Check me on that, Ethan. Isn't that right? Yeah, that's right. About 2. Close enough. Times 0.0167. Yeah, that's about 2. Okay, does that make sense? How we got that? What'd you get? I'm sure that's it. Yeah, that's guaranteed that's it. That can't be right.
You put .0. Oh, whoops. Yeah. So I added. No, you're right. It's about 2.
Yeah, about 2. Yeah. Okay, so, and I'm not sure. Again, it's possible. I might have not done all that mental math right. So but if I did it wrong, I mean, you could do it on a calculator and do it right. But you get the idea, right? Okay. All right, that's probably good for today. Is that enough math for you? You think?